Imagine a region of the universe where the rules you trust most simply stop applying. Black holes are the ultimate cosmic nightmare precisely because they shatter every instinct tied to survival. You can't escape them, you can't hide. And once you cross an invisible frontier known as the event horizon, even light, the fastest thing in existence, loses its freedom. It's like tumbling over the rim of an endless cosmic waterfall, except the plunge isn't through water but through the very fabric of space and time. What makes black holes so profoundly terrifying is how intimately they intertwine with matter. They are born when enormous stars collapse under their own weight, squeezing unimaginable mass into a space smaller than a modern city. The result? A gravitational force so extreme that it bends reality around it. Picture space as a stretched rubber sheet and a black hole as a bowling ball pressed into its center, forming a deep pit that everything nearby inevitably rolls into. But the truly unsettling part is this: black holes aren't rare. Astronomers estimate that the Milky Way alone hides about 100 million of them, most between 5 and 50 times the mass of our Sun. They drift silently between the stars, invisible except for the havoc they wreak on anything caught in their gravity. The terror deepens when you understand how they feed. As matter spirals inward, friction heats it until it burns brighter than entire civilizations. This process creates an accretion disk, a swirling maelstrom of superheated gas extending millions of miles. Temperatures here surpass 10 million degrees Fahrenheit, hot enough to rip electrons from atoms and forge a plasma inferno capable of annihilating any material instantly. More disturbing still is the way black holes distort time itself. As you approach the event horizon, time begins to stretch. To an outside observer, you would appear to slow, then freeze in place, your image fading as your light stretches into longer wavelengths until it disappears entirely. Yet from your own perspective, time would continue normally as you plummet toward the singularity. And that singularity is the most terrifying idea in physics, a point where all the mass of the black hole is compressed into infinite density, where space-time curves without limit, and where our scientific understanding simply breaks. Our equations, our theories, everything we know fails here. But black holes are not merely destroyers, they are cosmic architects. Nearly every large galaxy, including our Milky Way, anchors itself around a supermassive black hole, cosmic engines shaping structure and evolution. The monster at our galaxy's heart weighs 4 million suns.
The stellar graveyard around us is filled with horrors beyond imagination. Every black hole begins as a star, but only the most massive giants, at least 8 times heavier than the Sun, are destined for such violent futures. When these stars burn through their nuclear fuel, their collapse is catastrophic. The core implodes in less than a second, triggering a supernova powerful enough to outshine an entire galaxy. What survives this stellar death is far more dangerous. The collapsed core reaches densities beyond comprehension. Imagine compressing the mass of Mount Everest into something smaller than a grain of sand. That's the level of extremity we're dealing with. Stellar mass black holes typically range from 5 to 50 solar masses, yet they occupy a region tinier than most cities. For example, the event horizon of a black hole with 10 solar masses is just about 60 miles across. Inside that small region lies a gravitational field strong enough to tear apart anything that ventures too near. Perhaps the most chilling truth about stellar mass black holes is how many of them exist and how close some may be. Although only about 50 have been confirmed or suspected, theoretical models suggest the Milky Way could contain 100 million, drifting through space like invisible predators. The closest black hole known to Earth lurks roughly 1,500 light-years away in the constellation Telescopium.
The black hole, known as HR 6819, carries a mass roughly 8 times greater than our Sun. While that may sound comfortably remote, in cosmic terms, it sits practically next door. Most stellar mass black holes hide in perfect darkness, but a few betray their presence through their appetite. When paired with a companion star, a black hole can quietly siphon material from its partner. The stolen gas spirals inward, forming a glowing accretion disk that radiates powerful X-rays. These X-ray binaries flicker like cosmic distress signals, exposing the invisible predator that feeds at their center. This feeding ritual becomes a slow, violent dance. A normal star, often very similar to our own sun, gradually loses its outer layers as the black hole strips them away. Over millions of years, the black hole may consume its companion entirely, leaving behind nothing but the gravitational scar of its existence. But perhaps the most unsettling truth is this: stellar mass black holes can remain active for trillions of years. Stars burn out and die. Black holes grow. Every particle they swallow increases their mass, expands their event horizon, and makes them even more dangerous to anything that drifts too close. And then comes one of the most horrifying consequences of all: your body turning into a noodle, stretched beyond recognition in a process known as spaghettification. It begins subtly as you approach the event horizon, but quickly becomes a nightmare of physics. Objects are stretched into long, impossibly thin strands, like cosmic spaghetti. The terror stems from a simple rule of gravity: it weakens with distance. If you fall toward a black hole feet first, the pull on your feet becomes vastly stronger than the pull on your head. For a stellar mass black hole, this difference escalates with terrifying speed. Imagine you're 6 feet tall, falling toward a black hole 10 times the mass of the sun. At roughly 400 meters from the event horizon, the gravitational difference between your head and feet becomes equivalent to hanging an 800-pound weight from your ankles. Your body begins to stretch as tidal forces overpower your structural integrity. Closer still, around 200 meters, the forces grow into the thousands of pounds. Bones crack, muscles tear, organs distort grotesquely. The process is neither quick nor merciful. It unfolds gradually, but inevitably. And stretching is only half the story. As your body elongates vertically, it compresses horizontally. The same tidal forces squeeze you from side to side, as though you're being fed through a cosmic pasta machine. The physics behind this are as chilling as the experience. For a human near a 10 solar mass black hole, the stretching forces can reach 6 million times Earth's gravity. No biological material can survive such torment. At the molecular level, your body comes apart.
Different black holes produce radically different outcomes. Smaller ones are far more lethal because their tidal forces increase sharply near the event horizon. A 3 solar mass black hole would spaghettify you long before you ever reach the horizon. A supermassive black hole, ironically, might allow you to cross the boundary intact, only for the tearing to begin deeper inside. Spaghettification doesn't discriminate. Spacecraft, asteroids, entire planets, anything wandering too close would be stretched into thin, glowing threads. Larger objects simply begin the process farther away because their size makes tidal differences noticeable sooner. Astronomers have actually witnessed this horror. When black holes shred stars, the resulting tidal disruption events produce some of the most spectacular and violent displays ever seen, as the star's material stretches into long streams of incandescent gas. And all of this happens before you even cross the universe's most terrifying boundary, the event horizon, the point of no return. Crossing this invisible frontier is the closest thing to signing your own cosmic death warrant. The event horizon surrounds every black hole like a spherical prison made of distorted spacetime. From the outside, it looks like empty air, but once you pass through it, your fate is sealed more absolutely than in any cage humanity has ever built. The name says everything. It marks the boundary beyond which no event can ever be witnessed by the outside universe. After crossing it, you are permanently cut off.
No message, no light, no information of any kind can escape to reveal what became of you. For a black hole 10 times the sun's mass, the event horizon lies about 60 miles from the center. That distance seems manageable until you remember that escape velocity there surpasses the speed of light. Since nothing can exceed that limit, nothing gets out. And the worst part? Crossing the horizon feels like nothing at all. No impact, no barrier, no sensation. You simply drift through what appears to be ordinary empty space. Space that happens to be curved so violently that escape becomes impossible. The true nightmare of a black hole becomes clear the moment you attempt to communicate with the outside universe. As you drift closer to the event horizon, the light you emit stretches into longer and longer wavelengths. It reddens, weakens, and slips beyond visibility. To anyone watching from afar, you appear to slow, then fade, until your final image freezes on the brink of the horizon, dissolving into darkness as your light stretches into oblivion. Yet from your perspective, nothing feels strange. Time flows as usual, but the outside universe accelerates wildly. Stars flare and die in bursts of brilliance. Entire galaxies twist and evolve. The cosmic microwave background becomes bluer, hotter, more energetic, eventually transforming into a lethal storm of gamma radiation, capable of annihilating any living thing. At the event horizon, space-time itself curves so violently that straight lines no longer exist. Every path, every possible direction, bends inward toward the singularity. Even light, which normally carves straight trajectories, spirals helplessly toward the center. And the horror grows with every particle that falls in. A black hole isn't a static object. It swells. Each atom consumed increases its mass and expands its event horizon outward. The larger it becomes, the farther its influence reaches, enlarging the cosmic trap that nothing can escape. But the event horizon is more than a boundary. It is the edge of what can ever be known. Beyond it, the familiar laws of physics collapse entirely. And in the heart of nearly every galaxy lurks a beast that pushes this nightmare to unthinkable extremes: the supermassive black hole. These titans are in an entirely different league of horror. Instead of weighing dozens of suns, they weigh millions or even billions. They anchor galaxies by sheer gravitational dominance, influencing the motion of stars across hundreds of thousands of light years. The smallest supermassive black holes contain the mass of 100,000 suns crushed into a region smaller than our solar system. The largest ever found exceeds 100 billion solar masses, containing more matter than the entire Milky Way combined. Stellar mass black holes look like harmless particles of dust by comparison. But size is only the beginning. Their hunger is legendary. As matter falls in, it accelerates to near light speed, heating to millions of degrees. Accretion disks around these monsters shine brighter than entire galaxies, forming quasars visible from across the cosmos. The regions around them become cosmic hellscapes. Gas and dust spiral inward, smashing into themselves so violently that they unleash radiation across the entire electromagnetic spectrum. X-rays, gamma rays, radio waves, all blasting outward with intensities capable of sterilizing planets from thousands of light years away. Their gravitational reach is equally terrifying. A supermassive black hole can bind entire star clusters, forcing thousands of stars into tight, dizzying orbits. Some stars move at thousands of miles per second, swirling in gravitational hurricanes no human mind can truly imagine. And even more disturbing, these monsters seem to regulate how galaxies grow. Observations show a tight link between the mass of a galaxy and the mass of its central black hole. Somehow, these cosmic predators control star formation on galaxy scales, acting like thermostats that govern the temperature and density of interstellar gas.
Their event horizons are colossal. The one inside Messier 87 spans 24 billion miles, large enough to swallow our entire solar system with room to spare.
and they are effectively immortal. While small black holes eventually evaporate through Hawking radiation, supermassive ones take longer than the age of the universe to decay. They will outlive stars, planets, and perhaps even space-time itself. Just 26,000 light-years from us lies our own galactic monster, Sagittarius A. It sits at the center of the Milky Way like a cosmic spider, weighing over 4 million suns. Its influence stretches across the galaxy, shaping the motions of every star and possibly every living being. We cannot see it directly. Thick clouds of dust block visible light, but astronomers have watched nearby stars whip around it in stunning arcs, accelerated to unimaginable velocities. Some of these stars travel over 5,000 miles per second, fast enough to cross the United States in under a second. One star, known as S2, swoops within just 8 billion miles of the event horizon, close enough for time itself to warp. As S2 swings past, its light stretches to longer wavelengths while climbing out of the gravitational well, providing breathtaking confirmation of Einstein's predictions. Sagittarius A star's event horizon spans 24 million miles, about the size of Mercury's orbit. Inside that region, the laws of physics unravel completely. Matter, energy, and information fall into a realm where space and time lose all meaning. Right now, the monster sleeps. Unlike many active galactic nuclei, Sagittarius A star feeds only occasionally, flaring briefly when small gas clouds or rocks fall inward. But sleep is not safety. These flares remind us that the beast is alive and hungry. Over billions of years, shifts in the Milky Way's structure could alter our solar system's orbit, pulling us closer to the heart of the galaxy. A major feeding event, a star or massive gas cloud falling into Sagittarius A star, could unleash radiation powerful enough to sterilize vast regions of the Milky Way. But supermassive black holes can do more than consume stars. They can fire them. Hypervelocity stars reveal one of the most terrifying behaviors of black holes. These stellar bullets race through space at over 1,000 miles per second, fast enough to escape entire galaxies. They are cosmic cannonballs launched by supermassive black holes after they tear binary star systems apart. When a pair of stars wanders too close to a black hole, its gravity rips the system in two. One star is devoured, the other is hurled outward at unimaginable speed. A gravitational slingshot with energies that dwarf anything humanity could ever produce. The fastest known example, S5 HVS1, blasts through space at over 1,700 miles per second, a velocity so extreme it defies comprehension.
This stellar projectile moves with such impossible speed that it could cross the entire diameter of Earth in under 8 seconds. This runaway star was hurled outward from the supermassive black hole at our galaxy center, and has been traveling for over 33 million years, covering nearly 200,000 light-years in that time. What makes hypervelocity stars especially disturbing is not their individual power, but their numbers. Astronomers have already confirmed dozens of them, with hundreds more candidates awaiting verification. Each one is evidence of a violent gravitational encounter, a moment when a supermassive black hole tore apart a binary system and fired one of the stars across the galaxy like a cosmic bullet. And recent discoveries introduce an even darker possibility. Not all of these stellar bullets come from the Milky Way. Some appear to originate from the Large Magellanic Cloud, a neighboring galaxy. This means its central black hole has been flinging stars toward us for millions of years. In effect, we may be sitting in the middle of an intergalactic firing range. But the threat of hypervelocity stars goes beyond their astonishing speed. These stars can severely disrupt any star system they pass through. Their gravity can destabilize planetary orbits, fling planets into deep space, or disturb comet reservoirs. A hypervelocity star passing within a few light-years of our solar system could jolt to the Oort cloud, sending a swarm of comets cascading toward the inner planets.
Their existence also highlights the eerie precision of black hole violence. To accelerate a star to such speeds without tearing it apart requires a perfect balance of gravitational forces. Too little force, and the star remains trapped. Too much, and it's shredded before escaping. Hypervelocity stars are evidence of black holes acting with frightening efficiency, cosmic weapons operating with surgical accuracy. Perhaps the most unsettling truth is that what we observe is likely only a tiny fraction. For every hypervelocity star we detect, there may be countless dark objects moving at similar speeds. Failed stars, rogue planets, shattered remnants of stellar corpses, invisible until the moment they strike something unfortunate. And then comes the most spectacular horror of all, watching black holes tear entire stars apart in slow motion.
Tidal disruption events are among the most dramatic and terrifying displays in the universe. These cosmic executions occur when a star strays too close to a supermassive black hole and is ripped apart by the same tidal forces that would spaghettify a human, only on a scale that defies all comprehension. The process begins when a star crosses the tidal radius. For a star like our Sun, approaching a 1 million solar mass black hole, this critical distance is roughly 100 million miles from the event horizon. At that range, the gravitational pull on the star's near side becomes stronger than the star's own ability to hold itself together. The death that follows is anything but quick. The star is stretched into a grotesque, elongated form as tidal forces pull harder and harder on its extremities. Its core struggles desperately to remain intact. Material streams away from both sides, unraveling into long ribbons of plasma that wrap around the black hole like glowing cosmic spaghetti. As this stellar material spirals inward, it heats to over 100 million degrees Fahrenheit. Friction between the layers of infalling gas generates an accretion disk that blazes with the light of billions of suns. For months, this feeding frenzy can outshine the entire host galaxy, creating a beacon of destruction visible from billions of light years away. The efficiency of this execution is chilling. Roughly half of the star's mass is swallowed by the black hole. The other half is flung outward at thousands of miles per second, forming expanding shells of hot gas that would obliterate any planetary system within dozens of light years. Astronomers have watched these cosmic deaths unfold in real time. In 2019, telescopes captured a tidal disruption event in a galaxy 650 million light years away. A star the size of our Sun was methodically dismantled over several months, its final agonies recorded across multiple wavelengths. But perhaps the most terrifying detail of all, these events are not rare.
Astronomers estimate that tidal disruption events occur in an average galaxy only once every 10,000 to 100,000 years. But with billions of galaxies in the observable universe, this means that somewhere every few seconds, a star is being shredded by a black hole. The radiation from these events travels across unimaginable cosmic distances, producing some of the brightest flares ever witnessed. A single tidal disruption event can release as much energy as our Sun will produce over its entire 10 billion year lifetime. Welcome to the most violent region in existence, the accretion disk of a feeding black hole. Cosmic hell made real. This swirling, luminous vortex forms from matter spiraling inward, but unable to fall straight into the abyss. Instead, it circles like water around a doomed drain, except this drain leads not to a pipe, but to oblivion. The spiraling material accelerates to breathtaking speeds, sometimes reaching 30% of the speed of light. Friction between layers of the disk creates temperatures that make even stellar cores seem cold by comparison. The innermost regions soar above 1 billion degrees Fahrenheit, hot enough to fuse any element in the periodic table. Here, matter becomes a sieving plasma, where electrons and nuclei part ways, creating a glowing sea of charged particles that radiates with the power of trillions of suns. The disk stretches outward for several light years. Even the cooler regions, at a few million degrees, would vaporize any material known to science. The temperature gradient creates a nightmarish spectrum, radio waves on the outskirts, X-rays nearer in, and gamma rays erupting from the blazing inner zones. But the most terrifying element of the accretion disk is its magnetic rage. Charged particles twist magnetic fields into knots of raw cosmic power. These fields can launch jets of plasma at nearly light speed, colossal cosmic flamethrowers stretching for millions of light years. The spinning black hole drags space-time itself around with it, producing an effect known as frame dragging. Near the event horizon, this force becomes so overwhelming that nothing can remain at rest. Even light is swept along, forming the ergosphere, a region where space and time lose their ordinary meaning.
The violence inside an accretion disk surpasses anything the human mind can imagine. Matter is torn apart by gravitational forces millions of times stronger than Earth's gravity. Radiation strips electrons from atoms. Fusion ignites on a scale no star can match. And the efficiency is monstrous. Stars convert less than 1% of their fuel into energy. Accretion disks can convert up to 40% of infalling matter directly into pure energy, making them the most powerful energy engines in the universe. Then comes one of the most psychologically disturbing aspects of black hole physics. Time becomes a weapon. As you fall toward a black hole, time dilation warps reality. At a distance of 10 event horizon radii, time slows only slightly. At 3 radii, it runs at half speed. At 2 radii, it drops to 1/3. And near the event horizon, time dilation approaches infinity. From your perspective, you move normally. To an outside observer, your motions crawl. Your voice deepens. Your light shifts toward darker wavelengths. Eventually, your image freezes at the horizon, reddening and dimming until it disappears entirely. Yet from your own point of view, you pass cleanly through the event horizon and continue falling. This creates an unsettling paradox. You cross the horizon, but no one will ever see you do it. Communication becomes impossible. Your messages arrive more slowly, increasingly stretched, distorted, and red-shifted. Eventually, your words fade into radio waves, then infrared, then nothing. Yet you continue to receive light from the universe outside. And what you see is horrifying. The cosmos accelerating. Stars are born and die in moments. Galaxies twist and evolve in the blink of an eye. The cosmic microwave background blue shifts into a deadly cascade of gamma radiation. You become trapped in a temporal cage. You can watch the universe age, but you can never speak back to it. Time dilation affects not only your perception, but your biology. Your metabolism slows. Your neural activity drags. Your aging process nearly halts from the outside view. It is the cruelest kind of immortality. You live longer only by becoming completely disconnected from reality. Black holes reveal a truth we once thought impossible. Time is not fixed. It can stretch, distort, and collapse under gravity's command, transforming a familiar constant into a fluid, merciless dimension.
Deep within the constellation of Canes Venatici lurks a creature so immense it outweighs our entire galaxy. TON 618 stands as the ultimate embodiment of cosmic terror, a hyperluminous quasar powered by one of the largest black holes ever detected. Its mass exceeds 40 billion suns, placing it among the most monstrous objects the universe has ever produced. The sheer scale is overwhelming. The event horizon of this titan stretches nearly 800 astronomical units across. You could place the entire orbit of Neptune inside it and still have room left over. Even at the speed of light, the journey across its diameter would take more than 6 hours. But TON 618's true nightmare is its appetite. It devours matter at a rate that defies imagination, swallowing the equivalent of an entire sun every single day. This relentless feeding fuels an accretion disk so brilliant it outshines 400 trillion suns. And despite its unimaginable distance, over 10 billion light-years away, its fury reaches us across the cosmos. The gravitational warping around this monster is extreme. Near the event horizon, tidal forces become strong enough to tear apart any known material long before it arrives. A human body would be stretched across thousands of miles in seconds, an obliteration beyond comprehension. Its age is equally chilling. The light we observe began its journey when the universe was under 1 billion years old. TON 618 was already a supermassive giant during the cosmic dawn. How such a monster grew so quickly after the Big Bang remains one of astrophysics' greatest mysteries. Its accretion disk forms a cosmic lighthouse, visible nearly from the edge of the observable universe. The disk, spanning several light-years, glows at temperatures exceeding 1 billion degrees, while magnetic fields twisted within it launch jets of plasma at nearly the speed of light. The gravitational influence of TON 618 extends astonishingly far. It could bind entire star clusters, even small galaxies, in its grasp, forcing them into orbit like cosmic insects circling a flame. Any system within thousands of light-years would endure lethal radiation and catastrophic tidal forces. And perhaps most disturbing of all, TON 618 might not be unique. It represents only one example of an ultramassive class of black holes that may be far more common than we once believed. Titanic structures that challenge every model we have for black hole formation. But even TON 618 pales beside another cosmic behemoth. In the heart of the Phoenix cluster lies a black hole so massive it defies every boundary of theoretical physics.
Phoenix A, the cosmic heavyweight champion. This monster may weigh 100 billion suns, the most massive black hole ever discovered. Located 5.7 billion light-years from Earth, Phoenix A outweighs some galaxy clusters, pushing the limits of what a black hole can be. Its size is beyond human comprehension. With a mass twice that of TON 618 and over 20,000 times that of the supermassive black hole at the center of the Milky Way, Phoenix A dwarfs every known black hole. If it replaced our Sun, its event horizon would stretch beyond Neptune's orbit. The boundary itself spans roughly 1,950 astronomical units, larger than entire star systems. Light traveling at 186,000 miles per second would still need over 13 hours to cross from one side to the other. Time itself distorts noticeably, even at that distance. What makes Phoenix A even more horrifying is its environment. It sits at the core of the Phoenix cluster, one of the most massive galaxy clusters known. This cluster contains thousands of galaxies embedded in a vast web of dark matter and ultra-hot gas. Phoenix A rests at the center like a cosmic spider, pulling everything toward it. It actively feeds on the superheated gas permeating the cluster, material heated to tens of millions of degrees. This nearly endless supply of fuel allows the black hole to grow continually. The feeding process powers radio jets that stretch for millions of light-years, punching cavities into the cluster's gas, scars so vast they can be observed from Earth. The existence of Phoenix A poses a profound astrophysical crisis. According to standard models, no black hole should be able to reach such tremendous size within the lifetime of the universe. Its presence forces scientists to revisit every assumption about the rapid growth of black holes in the early cosmos. The influence of Phoenix A is not local, it is cluster-wide. It regulates the temperature and density of gas across millions of light-years, effectively controlling star formation in thousands of galaxies. Phoenix A is not just a black hole. It is a cosmic architect, sculptor, destroyer, and ruler of an entire region of the universe.
Phoenix A's influence shapes the evolution of an entire cluster,
containing more mass than 10,000 Milky Way galaxies combined. And perhaps the most unsettling implication is this: Phoenix A may not be the upper limit. If the universe can produce a black hole weighing 100 billion suns, what prevents it from creating monsters even larger? We may one day discover black holes weighing trillions of solar masses, titans so large they dwarf entire galaxy clusters, redefining the scale of cosmic horror. When supermassive black holes awaken and begin to feed, they unleash destructive forces capable of sterilizing entire galaxies. These eruptions give rise to the brightest and most violent objects in the cosmos: quasars. A quasar is a supermassive black hole that has broken out of dormancy and entered a feeding frenzy. Its accretion disk burns with such ferocity that it outshines its entire host galaxy, becoming a beacon visible across billions of light years. The term quasar, quasi-stellar radio source, reflects how they first appeared as star-like points in early radio surveys, but their true nature is far more terrifying. They are galactic cores turned into cosmic weapons, where matter is converted into pure energy through the most efficient process known in the universe. A typical quasar radiates more power than 1 trillion suns. The most extreme quasars burn 10,000 times brighter than the entire Milky Way, which contains over 100 billion stars. This unimaginable luminosity comes from matter being torn apart and accelerated to near light speeds inside the accretion disk. Temperatures soar past 1 billion degrees Fahrenheit, transforming matter into a plasma in which atoms are stripped bare. The resulting radiation spans from radio waves to deadly gamma rays, an electromagnetic hurricane capable of sterilizing planets across thousands of light years. Many quasars also produce relativistic jets, narrow beams of plasma blasting from the black hole's poles at over 99% the speed of light. These cosmic lances can extend for millions of light years, punching through intergalactic space like reality-shattering laser beams. Each jet carries as much energy as millions of stars
combined. The radiation from quasars is so intense that it can shut down star formation across their entire galaxies. Their energy heats and disperses the cold gas needed to form new stars, creating dead galaxies populated only by aging stellar remnants. This process, known as quasar feedback, can silence a galaxy for millions of years. Even more frightening, quasars were far more common in the early universe. Their population peaked when the cosmos was only a few billion years old, meaning the young universe was filled with these cosmic death rays. Their most lethal emissions, high-energy X-rays and gamma rays, penetrate deep into atmospheres, destroying ozone layers and annihilating biological life. But their most terrifying trait is their unpredictability. A dormant supermassive black hole can reactivate instantly if a new source of matter wanders too close, turning a peaceful galaxy into a cosmic weapon almost overnight. And yet, even quasars pale in comparison to what happens when two black holes collide. When black holes spiral together, they unleash the most violent events since the Big Bang: binary black hole mergers, catastrophes so extreme they shake the very fabric of the universe. These mergers release more energy in gravitational waves than all the stars in the observable universe emit in light. The process begins with two black holes orbiting each other in a deadly dance, sometimes for billions of years. As they rotate, they lose energy through gravitational radiation, drawing ever closer. Their speed increases until, in the final heartbeat before collision, they whip around each other at nearly the speed of light. Then comes the final moment, a merger lasting less than a second. But in that blink of time, 3 suns worth of mass is converted into pure gravitational energy. This energy ripples outward as waves in spacetime, traveling across the universe at the speed of light. When these waves pass through Earth, they stretch and compress space by amounts smaller than 1/10,000th the width of a proton, yet they originate from the most violent forces ever recorded. The most massive black hole merger detected so far involved black holes of 85 and 66 solar masses. Their collision produced a final black hole of about 140 solar masses, meaning that 11 suns worth of matter vanished in an instant, transformed entirely into gravitational waves.
But the terror doesn't end there. These mergers can devastate anything in the surrounding region. Their gravitational waves can disrupt star systems for hundreds of light years, triggering supernovae or ejecting planets from orbit. Spacetime becomes so distorted that the ordinary laws of physics temporarily break. And then comes the gravitational wave kick. If the merging black holes have misaligned spins, the final black hole can be launched like a cosmic cannonball at speeds exceeding 1,000 miles per second, fast enough to escape its galaxy entirely. A supermassive black hole flung into intergalactic space? A rogue singularity wandering the void? A monster without a home?
A gravitational wave kick can create a rogue black hole launched into interstellar space at hypervelocity. This runaway monster drifts through the cosmos like a silent cosmic torpedo, capable of disrupting star systems, scattering planets, and warping spacetime around anything unlucky enough to cross its path. Even more disturbing is the possibility that black hole mergers can trigger the formation of new black holes. When two black holes collide, the shock waves they send through surrounding gas clouds can compress the material, causing it to collapse. This chain reaction may create multiple new black holes. One merger becomes many, a cosmic cascade. And these catastrophes occur far more frequently than once believed. Modern gravitational wave detectors now observe roughly one binary black hole merger per week, implying that colossal black hole collisions are happening constantly throughout the universe. When black holes collide, the universe itself seems to cry out. Gravitational waves are the universe's most ancient, most primal form of communication. Ripples in space-time carrying messages of unimaginable violence across billions of light years. These waves race outward at the speed of light, stretching and compressing space-time as they propagate. When they finally wash across Earth, they reveal long-forgotten catastrophes that unfolded eons before humanity existed. Detecting these waves required constructing the most sensitive instruments ever built. The Laser Interferometer Gravitational Wave Observatory, LIGO, uses laser beams to measure changes in distance smaller than 1/10,000th the width of a proton. This superhuman precision allows scientists to detect the tremors of black hole collisions billions of light years away. Each gravitational wave detection is a story of destruction encoded in the fabric of reality. These ripples contain information about the masses, spins, and orbits of the black holes, as well as the energy released during their violent union. By reading these waves, scientists can reconstruct the entire merger, watching two titanic objects spiral inward before merging in a flash of gravitational fury.
The first detection, GW150914, revealed the collision of two black holes weighing 36 and 29 solar masses. This event happened 1.3 billion years ago, when multicellular life on Earth was just beginning to emerge. The gravitational waves from that ancient explosion traveled across space for more than 1 billion years before gently brushing past our planet. Black holes normally emit no light, hiding themselves from traditional telescopes. But gravitational waves expose their collisions even when these events occur behind thick clouds of dust or in distant regions of the universe. The energy released is staggering. A single black hole merger can emit more energy in gravitational waves than all the stars in the observable universe produce in light. These waves ripple through space, carrying the unmistakable signature of the catastrophe across unimaginable distances. The detection of gravitational waves has revealed a shocking truth. Black hole mergers occur far more frequently than we thought. The universe experiences these cosmic collisions at a rate of roughly 1 per minute, meaning space-time is constantly trembling under the weight of collapsing giants. And gravitational waves may represent only the beginning. The universe could be filled with other, still undetected distortions, interactions between dark matter particles, neutron star collisions, or even signals from the cosmic expansion itself. These invisible forces may carry secrets that lie completely outside our current understanding. Gravitational waves have given us a new way to sense the universe's most violent events, but they've also revealed the presence of hidden cosmic forces shaping reality on the grandest scales. And now we turn to one of the strangest and most unsettling of these forces. Something colossal and unseen is pulling our galaxy toward an unknown destination. Deep in the zone of avoidance, concealed behind the Milky Way's dusty disk, lies a gravitational anomaly so massive, so inexplicable, that it challenges everything we know about cosmic structure. This mysterious force is known as the Great Attractor, and it remains one of the most disturbing enigmas in modern cosmology.
A hidden region of space containing the mass of tens of thousands of galaxies lies shrouded behind a cosmic curtain. Invisible to our telescopes, this gravitational behemoth lurks roughly 250 million light-years away in the direction of Hydra. Its pull is so immense that it alters the motions of galaxies across hundreds of millions of light-years, including our own Milky Way. We are falling toward this unseen mass at over 400 miles per second, dragged by a force we barely understand. The Great Attractor reveals itself not through light, but through motion. According to Hubble's law, distant galaxies should flee from us with speeds proportional to their distance. Yet observations show something different. Galaxies across a vast region of space are flowing toward the same mysterious point, as if being pulled by a gravitational titan hidden behind the Milky Way. The terror lies in its invisibility. The Great Attractor sits behind the zone of avoidance, a swath of sky smothered by the dust and gas of our galaxy's disk. This cosmic fog blocks our view, preventing us from seeing what lies beyond, leaving a massive blind spot in our map of the universe. Only recently have radio and X-ray telescopes pierced this veil, revealing tangled structures of galaxy clusters and superclusters. The Great Attractor appears linked to the Norma cluster, a colossal congregation of galaxies that likely contains several supermassive black holes. But even this visible matter cannot account for the gravitational pull shaping such a vast region. The most disturbing possibility is that the Great Attractor is composed largely of dark matter, an invisible mass far greater than anything previously discovered. Dark matter makes up roughly 85% of the universe's mass, yet emits no light. A massive dark matter halo could explain the gravitational effects while remaining completely undetectable. Its influence stretches beyond our local galactic neighborhood. Entire clusters, containing thousands of galaxies, are drifting toward this hidden mass, forming a cosmic river of motion that spans hundreds of millions of light-years. This suggests that the Great Attractor may be only one piece of an even larger structure directing the flow of matter across the universe. The most unsettling implication is that our galaxy's ultimate fate may be tied to this invisible giant. Over cosmological timescales, the Milky Way may be pulled into a region where gravitational forces grow strong enough to tear apart its structure. But even this colossal enigma may not be the most ancient horror lurking in the cosmos. In the first second after the Big Bang, the universe may have created monsters that still wander unseen. Primordial black holes, cosmic relics older than stars, galaxies, and perhaps even the particles that form ordinary matter.
These ancient black holes did not form from collapsing stars. They were forged directly from violent density fluctuations in the newborn universe. In regions where matter briefly compressed beyond a critical threshold, space itself collapsed into black holes, long before the first atoms ever formed. Primordial black holes could span an astonishing range of sizes, from masses smaller than an asteroid to millions of suns. What makes them particularly terrifying is the possibility that they are everywhere. Some models propose that primordial black holes may constitute a significant fraction of dark matter.
If true, then the universe could be filled with billions, even trillions of invisible black holes drifting in the space between stars. They may exist in the outer solar system or pass silently through Earth itself. The smallest primordial black holes could weigh as much as mountains, but be smaller than atomic nuclei, essentially microscopic singularities impossible to detect directly. Yet their gravity could still perturb the orbits of planets or send comets hurtling toward Earth. Intermediate mass primordial black holes pose an even greater threat. Weighing from 1,000 to 100,000 suns, these monsters sit between the stellar and supermassive categories. One passing through the Milky Way could disrupt star formation, trigger supernovae, or fling entire star systems into intergalactic space. The most chilling truth is that primordial black holes would remain completely invisible until they encountered matter. They produce no accretion disks, no radiation, no detectable signals, unless they pass near something to devour. The search for these ancient objects has become one of modern astrophysics' most urgent quests. They may hold the answers to dark matter, the formation of the first galaxies, and the long-term destiny of the universe. But primordial black holes are not the only missing pieces of the cosmic puzzle. The universe hides a mysterious population of missing link black holes, objects that may bridge the gap between the black holes created by dying stars and the supermassive giants lurking in galactic cores. And we are only just beginning to find them.
Intermediate mass black holes, weighing between 100 and 100,000 suns, should exist in vast numbers throughout the universe, and yet they remain maddeningly elusive. This missing population has become one of the great cosmic horror stories because these black holes may be hiding in plain sight. Unlike stellar black holes, which betray themselves with X-rays from companion stars, or supermassive black holes, which power quasars and active galactic nuclei, these intermediate giants could drift invisibly through the darkest regions of space, leaving almost no electromagnetic trace. The few that have been discovered hint at their terrifying potential. One candidate, 3XMMJ215022.4, contains roughly 50,000 solar masses and lies on the outskirts of a distant galaxy. It appears to be slowly consuming a nearby star, producing periodic X-ray flares that momentarily reveal the presence of an otherwise unseen monster. What makes intermediate mass black holes especially dangerous is their mobility. Supermassive black holes are anchored deep within galactic centers, but intermediate mass black holes can be kicked loose, wandering the universe as rogue predators. They may have been ejected by gravitational encounters or hurled into intergalactic space by asymmetric gravitational waves during mergers. Their origins remain deeply unsettling. They may arise from the direct collapse of the universe's first stars, repeated mergers of smaller black holes, or the growth of primordial black holes formed moments after the Big Bang. Each scenario implies a different and frightening population of black holes lurking unseen in the cosmic night. Even worse, they might be hiding inside globular clusters, ancient, densely packed spheres of hundreds of thousands of stars. Within these tightly bound environments, repeated stellar collisions could seed the birth of intermediate mass monsters. Discovering this class of black hole would fill the long-standing gap between stellar and supermassive black holes, but it would also confirm that the universe contains a vast population of invisible predators. These objects could outnumber both known black hole types, forming a hidden ecosystem of destruction across the cosmos. The hunt has intensified in recent years thanks to gravitational wave detectors, which now provide a new way to uncover these missing link monsters. Future observatories may reveal that intermediate mass black holes exist in numbers far greater than we ever imagined. Wandering through the darkness are black holes shot from their galaxies like cosmic bullets. These are the rogue black holes, the most nightmarish class of all. They combine the destructive power of black holes with the unpredictability of hypervelocity objects moving at thousands of miles per second.
The ejection process is violent. When galaxies merge, their central black holes can engage in a gravitational duel. Sometimes, the slingshot effect sends one black hole speeding away at escape velocity, transforming it into a lone wanderer. The horror lies in their invisibility. Without accretion disks or bright radiation, rogue black holes are completely dark. They reveal themselves only when they pass in front of background stars, producing brief gravitational lensing events, fleeting distortions in starlight. Scientists estimate that billions of rogue black holes may drift through intergalactic space. Each one carries the gravitational memory of ancient collisions, traveling through the cosmos like cannonballs fired in galactic wars. Their danger goes far beyond simple destruction. A rogue black hole passing through our galaxy could disrupt the orbits of stars, flinging some out of the Milky Way entirely. If one passed through the outer solar system, it could disturb the Oort cloud, unleashing a storm of comets toward the inner planets. Some mergers observed by gravitational wave detectors may involve rogue black holes that spent billions of years wandering the void before encountering another massive object. Even more disturbing is the possibility that rogue black holes are far more common than we assumed. In the early universe, when galaxy formation was chaotic, slingshot ejections may have occurred constantly. This implies that intergalactic space could be populated by a vast, unseen swarm of gravitational predators. And their speed makes them uniquely terrifying. A rogue black hole could cross the entire solar system in just a few months. We would detect it only moments before it began tugging at the orbits of distant objects, far too late for any meaningful response. The existence of rogue black holes forces us to rethink the nature of cosmic safety. Space is not empty. It is full of invisible monsters, any one of which could emerge from the darkness without warning. Yet even rogue black holes pale beside the universe's most devastating weapon. Relativistic jets, million light-year death beams. Some black holes unleash jets of plasma that extend for millions of light years, sterilizing entire regions of space. These relativistic jets are among the most destructive forces known, carrying more power than entire galaxies. They begin with the spin of the black hole itself. A rotating black hole drags space-time with it, a phenomenon called frame dragging. This effect, combined with the intense magnetic fields of the accretion disk, creates a cosmic dynamo that accelerates charged particles to 99% the speed of light. The jets erupt from the black hole's poles as narrow, focused beams. The particles inside these jets experience extreme relativistic effects, time dilation, length contraction, such that millions of light years pass in what feels like moments. Their energy output is staggering. A single galactic jet can emit more energy than billions of stars, concentrated into a beam only a few thousand light years wide. This energy heats intergalactic gas to over 100 million degrees, carving cavities in the cosmic web that X-ray telescopes can detect from Earth. But the true horror lies in their reach. Relativistic jets can influence entire galaxy clusters. When a jet slams into the hot intergalactic medium,
It produces shock waves that sweep outward at thousands of miles per second, reshaping the cosmic environment. These jets are the universe's closest equivalent to weapons of mass destruction, not aimed by intention, but unleashed by gravity, spin, and magnetic fury.
The shock waves produced by relativistic jets ripple across intergalactic space, reshaping entire regions of the cosmos. In some locations, they compress clouds of gas, triggering new bursts of star formation. In others, they heat and disperse the gas, shutting star formation down entirely. In this way, black hole jets act like cosmic architects and executioners, sculpting galaxies across millions of light years. These jets also inflate enormous radio lobes, vast bubbles of high-energy particles that glow in radio wavelengths. Some radio lobes grow larger than entire galaxies, lingering for millions of years long after the jets shut down. Any planet unlucky enough to exist inside one of these lobes would be blasted with radiation powerful enough to sterilize all life. What makes these cosmic weapons even more terrifying is their directionality. Although relativistic jets are narrow beams, their aim can change over time as the black hole's spin axis slowly wobbles, a process called precession. Regions of space once safe from the jet's deadly radiation may suddenly find themselves exposed. The discovery of jets extending over 100 million light-years reveals their truly staggering reach. These ultra-long jets carve tunnels through the cosmic web, redistributing matter and energy on scales that dwarf entire galaxy clusters. This transforms black holes from mere gravitational monsters into universe-shaping engines, capable of altering cosmic structure on the grandest imaginable scales. Deep within the Phoenix cluster, a supermassive black hole demonstrates just how catastrophic this feedback can be. The Phoenix cluster is a cosmic laboratory, a vast structure 5.7 billion light-years from Earth, containing some of the most extreme examples of black hole-driven galaxy regulation ever observed. At its center lies Phoenix A, a supermassive black hole launching radio jets that stretch for millions of light-years. These jets carve enormous cavities into the superheated gas between galaxies, creating bubbles of low-density plasma detectable across the electromagnetic spectrum. The energy required to sculpt these cosmic caverns is staggering. Phoenix A expels roughly 10 to the power of 45 joules every second, the power of 10 billion suns. This energy floods the intergalactic medium, heating it to temperatures exceeding 100 million degrees Fahrenheit. The jets prevent the cluster's gas from cooling, stopping it from condensing into new stars. Entire galaxies within the cluster are left barren, filled only with old, dying stars. The Phoenix cluster shows how a single supermassive black hole can regulate star formation across thousands of galaxies, exerting environmental control on cluster-wide scales.
Even more frightening, the jets generate pressure waves traveling at thousands of miles per second. These waves can ignite star formation in some regions while extinguishing it in others, sculpting the stellar landscape across millions of light-years. The implications for our own galaxy are sobering. If Sagittarius A star, the Milky Way's central black hole, were to ignite jets similar to Phoenix A, our entire galaxy could be affected. Star formation could shut down. Much of the Milky Way could be bathed in lethal radiation. Worse still, the Phoenix cluster may foreshadow the fate of all galaxy clusters. As black holes grow through mergers, accretion, and cosmic evolution, they may eventually reach masses large enough to control or extinguish star formation across entire clusters. The late universe could become a graveyard of dead galaxies, their gas sterilized and their stars fading into darkness. The Phoenix cluster proves that black holes are not just local dangers. They are cosmic-scale forces capable of reshaping the structure and destiny of the universe, and in the far future, their power will grow beyond anything we can presently imagine. As the universe expands and cools, star formation will cease. Galaxies will merge. Supermassive black holes will consume stars, dust, gas, and most importantly, each other. Over trillions of years, black holes will continue to grow, feeding on whatever matter remains within reach. Cosmic expansion will bring more and more material into the grasp of these titans. Current models predict that in the deep future, when the universe is 10 times its current age, the largest black holes may weigh over 100 trillion solar masses. These hyper-colossal black holes will have event horizons spanning light years, large enough to engulf entire star systems. Their gravitational influence will extend across hundreds of thousands of light years, dominating the dynamics of entire galaxy clusters. As they consume more matter, their reach will expand. Galaxies will spiral toward them, falling in over timescales of hundreds of billions of years. The resulting accretion disks will be larger than modern galaxy clusters, glowing with temperatures and luminosities dwarfing everything we observe today. Jets of plasma will stretch for billions of light years, sterilizing entire cosmic regions and reshaping the structure of the universe. Eventually, these titanic black holes will begin to merge, creating gravitational wave events so powerful they may distort spacetime on truly fundamental levels, perhaps even altering the laws of physics themselves. The collision of two such stupendous black holes would release more energy than the Big Bang, a gravitational supernova reshaping the cosmos. Ultimately, this process may lead to the formation of a single black hole encompassing the entire universe, a cosmic singularity containing all matter, energy, and space-time within a single boundary. Its event horizon would be larger than the observable universe today, the final triumph of gravity over all other forces. The timescales are mind-bending, trillions of years, then quadrillions, then numbers beyond meaning. Yet the outcome appears inevitable, a future in which the universe becomes one all-consuming black hole, a single monster devouring everything that has ever existed. And, chillingly, there may already be black holes in the universe so massive that they defy our current understanding of physics.
Stupendously large black holes represent the theoretical ceiling of cosmic terror. Entities so massive, they test the very limits of gravity, space-time, and our understanding of the universe itself. These titanic monsters would weigh more than 100 billion suns, making them larger than entire galaxy clusters and approaching the mass of the observable universe. Their existence would require formation mechanisms utterly beyond anything known today. Traditional growth, collapsing stars, galactic mergers, accretion, simply cannot produce objects of this magnitude within the universe's current lifespan. Such behemoths would need to originate from the direct collapse of entire regions of the primordial universe, or from exotic processes involving dark matter, dark energy, or physics not yet discovered. A stupendously large black hole with a mass of 1 trillion suns would have an event horizon spanning over 100 light years, wider than the distance from the Sun to Alpha Centauri. Its gravitational influence would bind entire galaxy clusters, forcing thousands of galaxies to orbit like electrons around a cosmic nucleus. The tidal forces near such a monster would operate on a galactic scale. Approaching galaxies would stretch and warp, unraveling into luminous streams of stars and gas, spiraling into the accretion disk, a cosmic dismantling visible across millions of light years. The accretion disk of such a black hole would be unlike anything that exists today, a leviathan structure spanning hundreds of thousands of light years, containing the mass of millions of galaxies and glowing with the intensity of quadrillions of suns. The magnetic fields generated by this rotating sea of plasma would accelerate particles to energies approaching the theoretical limits of physics. And perhaps most disturbing, such monsters could already exist,
hidden within the cosmic web, masquerading as dark matter concentrations, or concealed behind the glow of the cosmic microwave background. Their discovery would revolutionize physics. They would push general relativity to the breaking point and expose entirely new laws governing matter, energy, and space-time. The gravitational waves produced by mergers of stupendously large black holes would carry energies capable of influencing the expansion of the universe itself. These cosmic collisions might explain the mysteries of dark energy, perhaps even the accelerating expansion of space. Their existence would raise profound questions about the fate of the cosmos. If such titans already roam the universe, they may represent the final form of all matter and energy, the ultimate destination of cosmic evolution.
Black holes will outlive stars, galaxies, and possibly the universe itself in a cosmic game of last survivor. The connection between black holes and the heat death of the universe is the ultimate cosmic horror. While the universe marches toward maximum entropy, black holes persist, growing, merging, consuming, long after every galaxy has faded into eternal night. When the universe reaches 10 to the 14th years, star formation will be long extinct. The last red dwarfs will flicker into cold remnants. Galaxies will merge into swollen ellipticals. The only remaining energy sources will be the occasional collision of dead stars and the slow, relentless feeding of supermassive black holes. In this dark age, black holes will dominate everything. They will continue to absorb gas, dust, rogue planets, and stellar corpses, growing ever larger. Their mergers will be the final fireworks of the dying universe, producing gravitational waves that echo through cosmic emptiness. But even black holes are not immortal. Eventually, they begin to evaporate through Hawking radiation, a quantum process that causes them to leak energy back into space. Yet this evaporation is unbelievably slow. A black hole with the mass of our sun would require 10 to the 67 years to evaporate. Supermassive black holes will persist for 10 to the 100 years or more. Black holes will survive through epochs when protons have decayed, when the cosmic microwave background has faded to zero, and when galaxies have been stretched into oblivion by the expansion of space. In this far future universe, black holes will be the final engines, dripping out the last traces of usable energy. As they shrink, Hawking radiation accelerates. The smaller a black hole becomes, the hotter it gets. Its final moments arrive in a violent crescendo. In the last second of its existence, a black hole radiates more energy than the sun emits over its entire 10 billion year lifespan. A final burst of gamma rays, a last scream, briefly illuminates the darkness before fading forever. The final black holes will be the smallest primordial ones, microscopic structures containing the mass of mountains. Their final evaporation will mark the absolute end of organized matter. After the last black hole evaporates, the universe will enter its final state. A cold, empty expanse filled only with stray particles and fading photons. The temperature approaches absolute zero. Matter becomes so diluted that collisions between particles may never happen again. This is the heat death of the universe, the triumph of entropy. And yet, even this may not be the true end. Some physicists propose that black hole evaporation is not destruction, but revelation. That the information swallowed by black holes, the histories of stars, planets, civilizations, is released in encoded form during their final explosions. The universe's last act may be the unveiling of its secrets, a final cascade of Hawking radiation containing the memory of everything that ever existed. The terror of black holes lies not only in their ability to destroy, but in their role as cosmic archivists.
They preserve the information of everything they consume, guarding it within their event horizons until the end of time. When the final black hole evaporates, it may release this cosmic library into the dying universe, a final monument to all that once was, a last whisper before the darkness claims all.